Good day everyone, I am Marvi Katuiran, Bsed Mathematics, second year Set A. The matrix has a long history of application in solving linear equations. They were known as arrays until 18,000s. The term matrix, Latin word for womb derived from mater to mother, was coined by James Joseph Silvester in 1850. Who understood a matrix as an object giving rise to a number of determinants today called minors. That is to say, determinants of smaller matrices that are derived from the original one by removing columns and rows.
So, good day everyone. I'm Christian P. Jagbel from Bsed Mathematics 2A. So, what is the determinants of matrix product? Let's start with the determinants. It is a factor which decisively affects the nature of outcomes of something. For a matrix product, particularly in linear algebra, matrix multiplication is a binary operation that produces a matrix from two matrices. The matrix product has the number of rows of the first and the number of columns of the second matrix.
My name is Chana Bijana from Bsed Math 2A. So we will now proceed to the examples of determinants of matrix products. So what are the examples of determinants of matrix product?
Matrix A, which is equal to 0, and the determinant of matrix B, which is equal to 24. Now we're going to find the determinant of the product of A and B. First matrix, negative 1, negative 1, 0, negative 2, and 3. That, again, we get a 3 by 3 matrix. And to find the first element up here, we multiply this row times the first column. That's minus 3, minus 4 is minus 7, plus 15, minus 7, plus 15 is plus 8. Now we're going to take the determinant of this product matrix, A times B, and it should equal the product of the determinant of A times the determinant of B. It would be 0 times 24, or 0. So the determinant of this matrix should equal 0. Let's see if that's true. So we're going to take the determinant of the product, A7, which is equal to, taking the first element, 8, times the minor matrix. These four elements right here are the minor determinant. That would be minus 9, minus 3, 1, and 9. Like this. Now let's go ahead and work that out and see what we get. This is equal to 8 times minus 81 minus a minus 3, that's plus 3. Minus 81 plus 3, that gives us minus 78. Okay, let's now hit and simplify that further. This is equal to, well, 8 times 80 is 640, but minus 16, that would be 624 minus 624. This times this, when you add all those together, indeed, you will indeed get 0. Which is what we get when we multiply the determinant of A times the determinant of B.
Hello. Here is the other property of determinant. Theorem 3.6. Determinant of a scalar multiple matrix. If A is a square matrix of order n and C is a scalar, then the determinant of scalar square matrix A is this. Determinant of a scalar square matrix A is equal to scalar to the n power determinant of square matrix A. Here is the given example of determinant of a scalar multiple matrix that will explain to us by Miss Kalim and Miss Dana.
So let's apply Theorem 3.6 to conclude that matrix A is equal to 10 raised to 3. So we have 1, negative 2, 4, 3, 0, 5, negative 2, negative 3, and 1. So 10 raised to 3, we are going to multiply 10 itself in 3 times. So 10 times 10 times 10 is equal to 1,000. So 1,000 times 5. 5 is our determinant of 3 by 3 matrix. So 1,000 times 5 is equal to 5,000.
Find the determinant of the matrix. Matrix A is equal to 3 by 3 matrix which contains this number. A is equal to 10, negative 20, 40, 30, 0, 50, negative 20, negative 30, 10. Is equal to 1, 0, 5, negative 3, 1, minus negative 2, 3, 5, negative 2, 1, plus 4, 3, 0, negative 2, negative 3 is equal to 1, 0 times minus negative 3 times 5 minus negative 2, 3 times negative 5 times negative 2 plus 4, 3 times negative 3 minus 0 times negative 2 is equal to 1, 0 plus 5 minus 0 minus negative 2 times 13 plus 4 times negative 9 is equal to 1 times 15 plus 2 times 13 plus 4 times negative 9 is equal to 15 plus 26 minus 36. So the matrix A is equal to 5.
Determinant of an invertible matrix. A square matrix A is invertible or non-singular if and only if determinant A is not equal to 0. So I will show you later on how to determine whether the determinant is not equal to 0.
So a square matrix A is invertible or non-singular if and only if determinant A is not equals to 0. And matrix A is invertible or non-singular if matrix A is an n by n matrix such that A times B is equals to B times A equals to I sub n, where I sub n is the identity matrix and B is the inverse of A, which is shown B is equals to A inverse. So let me show you first how to determine this determinant A, whether it is non-zero or not, using the diagonal method or rule of Saros. So first let's copy the matrix, which is 1, 3, negative 1, negative 2, 5, 3, 3, 2, and negative 4. So first, let us copy the first two rows, which is 1, 3, and negative 1, and negative 2, 5, and 3. So as you can see, there is this first diagonal from left side, which is 1, 5, and 4. Second one is negative 2, 2 to negative 1, and 3, 3, and 3. And there is this fourth diagonal, which is the negative 2 to negative 4, 1, 2 to 3, and 3, 5 to negative 1. So determinant A is equals to 1 times 5 times negative 4 is equals to negative 20, plus negative 2 times 5 is equals to negative 10 times negative 1 is equals to positive 10, plus 3 times 3 times 3 is equals to positive 27, and subtract with the another row, which is from start here is 3 times 5 is equals to 15 times negative 1 is negative 15.
So to find the determinant of invertible matrix, we have an example of 1, 2, 3, and 4. So we can use a diagonal method, which is 1 multiplied by 4 is equal to 4 minus 3 multiplied by 2 is equal to 6. So 4 minus 6 is equal to negative 2. Negative 2 are not equal to 0. So we can conclude that these matrices are invertible or non-singular because negative 2 are not equal to 0.
Good day, everyone. I am Elaine Pearl Tandangay Cavil. My task is to give an example about our chosen topic, which is the determinant of an invertible matrix. So, this is the example of determinant of an invertible matrix. So, E is equals to negative 6 to 4, then negative 10 to negative 11. So that determinant is equals to E is equals to negative 6 multiply the negative 11 minus negative 10 multiply 4 is equals to 66 minus negative 40 is equals to 106. So since the determinant is equals to 106 and it is not equal to 0, then the matrix is invertible. So this is the example of determinant.
Hello everyone, my name is Christian Del Pinto, Bsed Math, second year, Set A. And today, I'm going to discuss to you the Theorem 3.8 of the properties of determinant, which is the determinant of an inverse matrix. So if A is invertible, so the solution is the determinant of inverse A is equals to 1 all over by the determinant of A. We need to find the determinant of an inverse 3 by 3 matrix with this example. Now to find the determinant of a 3 by 3 matrix, we need to copy the original matrix and add the first two columns at the end of the original matrix, which is like this. To find the determinant of this 3 by 3 matrix, the first step we are going to do is to find the main diagonals, which is the first group is 2, negative 1, 2, the second group which is 1, 4, 1, and the third group which is 0, 3, 1. We need to multiply them and combine them by adding, which is like this. 2 times negative 1 times 2, which give us negative 4. 1 times 4 times 1, which give us 4. 0 times 3 times 1, which give us 0. So, when we add them together, the main diagonal is 0. The second step we are going to do is to find the second diagonals. To find the second diagonal, it just like the opposite of finding the main diagonals, which is we need to start here. So again, we need to multiply them together and combine them by adding, so that 1 times 3 times 2 is equals to 6. 2 times 4 times 1, which give us 8. 0 times negative 1 times 1, which give us 0. So the second diagonal is 14. In order to find the determinant of A, we must subtract the main diagonal with the second diagonal, which is 0 minus 14. Therefore, the determinant of matrix A given by a 3 by 3 matrix is equal to negative 14. The last step we are going to do is use the formula of determinant of an inverse matrix A is equals to 1 all over by determinant of A to conclude that the determinant of an inverse matrix A is equals to negative 1 over 14. I hope you have learned so much in this discussion, and that's all. Thank you.
Note that Theorem 3.7 provides another equivalent condition that can be added to the list in Theorem 2.15. The following summarize all 6 conditions. Equivalent condition for a non-singular matrix. If A is n times n matrix, then the following statements are equivalent. Number 1, A is invertible. Number 2, AX is equal to B has a unique solution for every n times 1 column matrix B. Number 3, AX is equal to 0 has only the trivial solution. Number 4, A is the row equivalent to inverse of n. Number 5, A can be written as the product of elementary matrices. Number 6, that A or determinant of A is not equal to 0.
Good morning everyone. So today we are having a determinant of an inverse matrix. So we have this formula. The inverse of A is equals to 1 over the determinant of A. So we have this example matrix. So first, in finding the inverse, find the determinant of A. So we have this formula. So copy the matrix. Then copy the first two columns, which are 105, 216. Then multiply the diagonals. And we come up to this answer. 0, 50, and 0. 15, 30, and 0. So for the next step, for finding the determinant of A, follow this formula. So we have this 0 plus 50 plus 0 minus 15 plus 30 plus 0. So we come up with the answer. determinant of A is equals to 5. And then, immediately, follow the formula of the inverse of A. So A raised to negative 1 is equal to 1 over the determinant of A. Then, substitute the value of A, which is 5. So the answer of A raised to negative 1 is equals to 1.
For the continuation of our lesson, that will be the Theorem 3.9 entitled The Determinant of a Transpose. First, let me introduce you what does transpose means.
And now, let's determine the meaning of transpose. Transpose is to interchange the rows and the columns. This is the example of transpose. We have a matrix A. It has 2 rows and 2 columns. If you transpose matrix A, this would be the answer. The first row of the matrix A would be the first column of the transpose matrix. The second row of the matrix A would be the second column of the transpose matrix.
As we already know what does transpose mean, this time we're going to talk about the lesson, which is the determinant of a transpose.
Everyone, now let's talk about the determinant of transpose. So what is the determinant of transpose? It is said that for any square matrix A, the transpose of determinant A is equal to the determinant A matrix. So, what is the determinant? First, what is determinant? Determinant is, example, in a 2x2 matrix, A, B, C, D is equal to AB minus BC, or the diagonal AB minus the diagonal BC. So, that is the determinant. Here we have an example. The determinant of this matrix A11, A12, A21, A22 is equal to the diagonal of here A11 times A22 minus A12 diagonal A21 here. And the transpose of this matrix is like this. The first row became the first column and the second row became the second column. And as we look at these two, we can see the only difference is the 21 and the 12. Here, from the determinant of this matrix, A12 and A21, while in the transpose, it became A21, A12. They exchange positions. So, it is equal to A11 times A22, which is the diagonal, minus the diagonal of A21 times A12. It is. We can write these terms into determinant of A by using the scalar multiplication commutativity. So we can write as A11 times A22 minus, they exchange, A12 times A21. So these terms is equal to the determinant of A. So we prove the theorem that for any square matrix A, the transpose of determinant A is equal to the transpose of A. Thank you.
By that explanation, this time I'm going to show you some videos of what is really the determinant of a transpose.
So for example, let A be, let A be 1, 2, 3, and 4. Okay. So if we take the transpose of that, okay. Alright, so taking the transpose of this matrix, okay, so that's going to be, so the columns become rows, and the rows become columns. So this is going to be 1, 3, and then 2 and 4. Okay, so the determinant of A here, this is going to be, again, 4 minus 6, that's going to be negative 2. Okay, the determinant of A transpose, okay, is going to be 4 minus 6 as well, so that's going to give us negative 2. So taking the transpose of a matrix doesn't affect the, does not change the determinant value. Okay? And that's the whole point of this theorem.
We are glad that you have watched our video, hoping that you have learned and inculcated some ideas in your mind about what is the determinant of a transpose. Thank you!